Warbeck and Elphys. Was done in the context of grid mapping, but that shouldn't bother us. Just consider that was a map. Why was this so easy to compute? This is true. We assumed independence of the grid source. This is absolutely right, but that was not the point I want to nail down here at the moment. There was another strong dependency that we exploited.
Because the map is static?
Yes, but we talk about static maps here as well. So the key underlying assumptions of this mapping algorithm was, once I know the poses of the robot, mapping is easy, right? So if we know where the robot is during data acquisition, mapping is easy. So that's exactly what we learned. Given we know the trajectory where the robot was during data acquisition, estimating the map is easy. So if I know where the robot is at every point in time, there is no post uncertainty of the system, and I just can continuously measure the landmarks and update their belief. There's not this mutual dependency between the pose of the robot that impact the landmarks and vice versa. I can simply easily break that up. So the key idea, what we now want to do, is to use a particle filter to only represent the poses of the robot. Then every sample is an individual trajectory estimate. Sample 1 says, okay, the robot went along here on this path. Sample 2 says, okay, the robot went here, but it went a little bit further there and then turned around. Particle number 3 says, okay, I walked down for a longer period of time and then turned left. Every of those samples assumes that it did the right job. That was the key idea of the particle filter. Every sample says, I did the right thing. So as a result of that, you can say, okay, one option is particle 1 did the right job. If particle 1 did the right job, the world will look like the trajectory of particle 1 applying mapping with known poses. Or particle 2 was right in estimating the current trajectory. Then I take particle number 2 and do mapping with known poses using the trajectory of particle number 2, and so on. So as a result of that, I have a distribution of possible maps that are generated conditioned on the samples, on the poses, sorry. So the key idea is now to use a particle filter to represent only the trajectories that the robot have taken, and then for every sample build an individual map using mapping with known poses, and say, if the trajectory of particle 1 was the right trajectory, then the world looks like this. Or particle 2 did the right job, then this was the trajectory, and then the map looks like the map that is generated using the trajectory of particle number 2, and so on. So compared to localization, where I kind of maintained a single x, y, theta location for every sample, I now have a trajectory, and to every trajectory you can see kind of there's attached a map. And this map is a result of that trajectory. And that's exactly what the particle filter, the so-called Rao-Blackwellized particle filter is doing. And this technique is something which is called Rao-Blackwellization. And mathematically, it's a very trivial factorization. That's just kind of the definition of the conditional probability that is exploited here. So given that I want to represent this distribution about, let's say, two random variables A and B here. And P of B given A, so this part over here, can be computed very efficiently. So given I know A, I can compute B easily. If this is the case, it can make sense to say, okay, let's represent only A with samples. And then for every sample, just compute P of B given A, given that I take exactly the state of A, which the sample told me. So for what does it mean for us here? For us, it means A is the trajectory of the poses of the robot, and B is the map. So I say instead of computing P of A and B, so P of the robot's poses and the map with particles, I say, okay, let's take only P of A, so the trajectory of the robot, use samples to represent that, and then for every sample, compute P of B given A, so the likelihood of the map given the trajectory in an efficient manner. That's kind of the key idea behind that. As a result of that, I need the samples only to cover the likely regions in A and not in A and B. And especially if we now think about A is low dimensional and B is very high dimensional, this is a great advantage. And that's exactly the key idea what the Rao-Blackwell particle filter for mapping does. So it starts out with the probability distribution about the poses and the map. So these are now M landmarks, capital M landmarks, given my observations and given my movements. It's kind of the standard thing. What it now does, it just factorizes this belief into two terms, namely P of x given these quantities here, so the observations and the controls, times P of m given x, the observation and the controls. So just split that up, just applying the definition of the conditional probability to separate that term into, so I have here P of x given the observations and the controls times P of the map given x, the observations. In theory, you have the controls in here, but we can actually ignore them if we know the poses. It's kind of so there are two steps in here. So ut should be u1 to t could be in here, but I can neglect that because once I know the poses, I'm not interested in the odometry commands anymore. So we have now two posteriors. The first one is path posterior, which estimates what's the trajectory that the robot took. And the second is a map posterior that depends on the possible paths that the robot has been taken. Okay? Okay, good. So the question is, how can we compute this term efficiently? And this is, again, as I said, mapping with known poses. Okay, so we discussed mapping with known poses in the context of grid map, but not that much in the context of, we did in the beginning in the EKF. Let's have a very, very quick look how we could do that. In order to do that, let's have a look to the graphical model that underlies this process. So this is a graphical model you have seen in probably the first lecture of this course. So we have here the poses of the robot, x, which I want to estimate. I have the landmarks down here, the observations, and the controls. So what this says is read these errors at influences. So you say xt minus 1 influences xt as well as ut influences xt. So this is exactly the motion model which sits in here. It's p of xt given xt minus 1 and ut. And these errors show kind of a direct dependence. The same holds. The current pose has an impact on what I'm going to observe, and also the location of the landmark has an impact on what I'm going to observe. This is how you can read that. And you can use these graphical models to, or in this case a Bayes network, to also express conditional independence or independence of variables. Okay, if we now say we know the poses of the system, right? That's what this in the, so we want to estimate this guy over here. We assume that we know all the poses. So all these guys up here are known. So all these variables are known. And as a result of that, you can't find any path from any landmark to another landmark which doesn't go through these known variables. So there's no way kind of to reach from M1 to go to M2, or from M2 to M3, or from M3 to M1, throughout passing through these known poses. And if this is the case, these variables are independent of each other. So what this results in is these landmarks are all independent of each other, given we know the poses of the system. It's not the official formal definition of independence in those graphical models, but for now, I would like to stick with this very simplified form. So at least if all passes from one variable to another variable are blocked, so to say, by a known quantity, then these variables are independent given these known quantities. This is exactly the case here. So there's no path from one landmark to another landmark given I know the poses. So for this